Okay.
Uh,
Can I carry on now?
yes. Could you just start again? Is it okay if you start again?
Okay. Well, thank you for this invitation. So we're talking about in the context of Kahler geometry, which is a relatively well understood area of differential geometry with many famous theorems on the existence of special structures, special Kahler metrics, including the Calabi-Yau metrics on manifolds with 0 first Chern class. So that will be one of the main foci of the talk. The other focus will be on what are called constant scalar curvature Kahler metrics. Another area that we won't actually talk about, but where the same techniques apply, is the study of Hermitian-Yang-Mills connections on holomorphic vector bundles. And then also things called extremal metrics, which we won't go into in detail, but again, the same techniques apply. So what I'm going to talk about is not new work by any means. Everything I'll say is essentially contained in these 3 papers from 10 or 15 years ago, or even more. So I could have given this talk quite a while back. Maybe many of you weren't around at that time, and maybe it will give some helpful background for other talks in this meeting. So just to recall what these equations are, the Calabi-Yau equation, it can be set up as a second order nonlinear PDE for a Kahler potential phi. That's to say, in terms of some reference metric, we describe any other Kahler metric in the same class in terms of a Kahler potential. And then the Calabi-Yau equation is actually a special case of a slightly different problem, which is to find a Kahler metric with a given volume form. So we have a given volume form mu, and we want to solve this equation that the top power of the Kahler form is equal to mu. Whereas the constant scalar curvature equation is, in a sense, more formidable. It's a 4th order PDE for the Kahler potential phi. But today we're not talking about existence theorems. In fact, I'll be quite vague about anything to do with actual theorems. What we're interested in is knowing something about the solutions which these existence theorems provide us with. For example, we can write down, if to take a typical polynomial, a degree 4 homogeneous polynomial in 4 variables. It defines a quartic surface in CP3, which, according to Yau's famous theorem, we know has a metric of 0 reaching curvature. But apart from knowing it exists, there's not much else that theory tells us about it. For example, we could ask, what is the diameter, or how large is the curvature? And we just don't know. I mean, even we might want to know these things fairly exactly, or we might just want to know roughly a kind of order of magnitude information. So I've got something about continue. Let's try that. But of course, I mean, these quantity, the metric we have depends upon the particular surface we have. It depends upon the particular polynomial that we take. Or from the point of view, it depends upon the point in the moduli space. So the context for this talk is that we're interested in finding numerical approximations to the metrics, which will give us information about these questions. So perhaps I should first say that I'm completely not an expert in anything to do with numerical methods. Everything I'll be saying will be completely amateurish in a sense. So anyway, just the kind of strategic questions about how we might go about this. One is, how can we approximate Kahler metrics in a way that we can feed them into a computer? Another is, if we have such a method, how do we find the approximations which give good approximations to the metrics we're interested in? So, otherwise, it's a particular case of the usual problem of finding a numerical approximation to a solution of a PDE. So for the first issue, what we're going to talk about will be using approximations given by projective embeddings. That's to say, we will always be talking about projective manifolds, X, which can be embedded in projective space. On projective space, we have the standard Fubini-Studi metric, and we want to consider what I'm going to call algebraic metrics, ones which can be obtained by the restriction of the Fubini-Studi metric under such an embedding. So to discuss this a bit more, I'm going to launch into a section of background in which I'll talk about some of the analysis and geometry relevant to these projective embeddings. So let's consider so abstractly our compact complex manifold X with an ample line bundle L over it, or a positive line bundle over it. And then we're going to consider the tensor powers L to the k for positive integers k. So on the space of holomorphic sections of this line bundle, we have, in the standard way, an L2 metric. Or more precisely, we can define an L2 metric in terms of two pieces of data. We want a fiber-wise Hermitian metric on the line bundle and a volume form on the manifold. If we have that, and we can do this for each value of k, then we have what's called the Bergman functions, which are real valued functions on our manifold, one for each k. Often people talk about the Bergman kernel, which is a function of two variables. So in that sense, we're just looking at the restriction of the kernel to the diagonal. Well, the Bergman function, one way of defining it is to say, take any orthonormal basis of our space of sections with respect to the L2 Hermitian metric, and then take the sum of the squares of the pointwise norms. And then you think for a moment, you see that this is independent of the choice of orthonormal basis. Another way of saying that is that the Bergman function at a point x is given by taking the evaluation map that evaluates sections at x. So we have an evaluation map from this vector space to a one-dimensional vector space. Both of them have got norms, and then the Bergman function is the square of the norm of that map. And notice that from the definition, if we integrate the Bergman function multiplied using our volume form mu, then we get the dimension of the space of sections. And in our context, at least when k is sufficiently large, that dimension will be given by the Riemann-Roch formula, something we know to write down in terms of topological invariance of the situation. So you can think of the Bergman function as giving the density of the holomorphic sections on the manifolds. The function is large, where roughly speaking, there are lots of holomorphic sections, or the holomorphic sections are big. the function is small, where it's harder to find holomorphic sections. So what does this have to do with projective embeddings? So again, taking K sufficiently large, we can suppose that X is embedded in the projective space, the projectivization of the dual of the space of sections by this intrinsic embedding. On the other hand, the L2 metric on the space of sections defines a Fubini-Studi metric on that projective space. So we get a Kahler metric on X by restricting the Fubini-Studi metric. And we'll divide that by K in order to normalize so that that's in the fixed Kahler class independent of K. So another thing we can do is to take the curvature of our Hermitian line bundle, LH, multiply that by I, or, yeah, and that gives a Kahler metric. And then the two are related by taking d bar d of the log of the Bergman kernel. So this essentially follows from the definition of the Fubini-Studi metric and the usual formula for the curvature of a Hermitian line bundle in terms of d bar d of the log of the norm of a local holomorphic section. So in our discussion, K, we'll be thinking as large. So we're interested in the asymptotic behavior of these Bergman kernels as K tends to infinity. So there are going to be two cases that are relevant. The first one, let's take the volume form, mu, to be also determined by H. So we take the Kahler form, omega, given by the curvature of our line bundle, and take mu to be the standard volume form associated to that. So then the statement is that this Bergman function has an asymptotic expansion as K tends to infinity of the following form. So the leading term is just K to the n, and then there are lower order correction terms where the coefficients are given by universal expressions in terms of the differential geometry of X with the Kahler metric omega H. So in particular, the only one that's really relevant to us is that the first coefficient is half the scalar curvature. So this is, I mean, there are many, this statement combines results of many people, all written down here. The identification of the term A1 with the half the scalar curvature is one of the results of Lu, and there are also results about these higher coefficients. So there's some similarity here with what's called the local index theorem, because we know that the integral of bk gives the dimension of the space of sections, and we know that's given by the usual polynomial given by the Riemann-Roch formula. So we know that the integrals of these AI are known expressions in terms of Chern classes and so forth. And those expressions have standard Chern-Weil representatives. And so it's not actually true that the AI just are those Chern-Weil representatives. They contain other terms which integrate to zero, but at least for the first term, that half the scalar curvature is just what you'd expect as the thing that integrates to give what you need in Riemann-Roch. So the first corollary of this is due to Tian, one of the early results of Tian, is that as k tends to infinity, these algebraic metrics that we've obtained by these projective embeddings, converge to the other metric, omega h. So this just follows from the fact that the leading term in this Bergman function is 1. And in fact, the two metrics differ by order k to the minus 2. So this tells us that any Kahler metric on our manifold, at least in this given class, the first term class of the line bundle, can be approximated arbitrarily well by algebraic metrics induced by embeddings of X and restrictions of the Fubini-Studi metric. So that's sort of the fundamental thing which makes our strategy one plausible. Let's just say, running throughout this, and familiar in other contexts, is that there are 2 points of view. One is that we can think of X being embedded in a fixed way in projective space, and then vary the Hermitian metric on the underlying vector space, and therefore, in that way, varying the Fubini-Studi metric on projective space. The other point of view, which of course is equivalent, is that we think of fixing the metric on Cn plus 1, and therefore fixing the Fubini-Studi metric on projective space, and then varying the embedding of X by moving it around using the action of projective transformations. So Chellen's result says we can approximate any metric to order k to the minus 2. In fact, I can show, starting from that and using this expansion, one can show that one can make better approximations. We could find, for any metric omega h, we can find a sequence omega k given by embeddings of degree k, using L to the k, which approximate omega h to arbitrarily high orders. The error is less than any k to the minus r as k tends to infinity for all r. So this is analogous to the fact that if you take a smooth function and look at the truncation of its Fourier series, then that approximates the function to infinite order. So this was the version discussed when we were using the volume form, which itself depended upon the Hermitian metric on the line bundle. A variant, which is, as we see, relevant to the Calabi-Yau problem, is to say, supposing we have some given volume form on X, mu, and then use that to define our Bergman kernel, and then we get a slightly different story, that the leading term of our Bergman function is not now 1, but involves the ratio of these two volume forms. And then there's some other slightly different set of coefficients that come in for the subsequent terms. So let's, how's the time going? Let's spend just a few moments saying something about why we should have that asymptotic expansion, which I'm calling star, star, star. So again, yet another way of thinking about this Bergman kernel, if we have a fixer point x in our manifold, then the value of bk at x is the square of the norm of a particular holomorphic section, which is sigma x, which is characterized by having L2 norm 1 and being orthogonal in the L2 sense to all sections which vanish at x. So this section is unique up to multiplication by a complex number of modulus 1. So if we do the same thing on, if we take Cn, which of course is not compact, but we take a Hermitian holomorphic line bundle, which in fact would be the trivial holomorphic line bundle, but with the Hermitian metric chosen so that the curvature form defines the standard metric on Cn. Then the same constructions make sense, and this sigma naught, the section associated to the origin, is just essentially sort of this Gaussian function. The norm of sigma naught has got this Gaussian function. So the crucial thing is it decays very rapidly at infinity in Cn. So in our asymptotics, we're interested in replacing L by L to the k, and then making k large. So when we do that replacement, we replace, if you like, the Kahler form omega h by k times omega h. So this is what defines our metric. So in metric terms, we scale lengths by a factor of the square root of k. So as k tends to infinity, if we use these metrics sort of naturally associated to the L to the k, the manifold becomes very large, and the geometry in a given neighborhood of X converges to the flat model, a given metric neighborhood. Then the idea is that when k is large, the section sigma x that we're interested in on X is a small perturbation of the section sigma naught in the flat model. And the essential reason why that works is the rapid decay, which makes everything localize around a small ball of radius approximately 1 over the square root of k about x. So all these terms, the AI, just measure the slight deviation from the metric of this rescaled ball, essentially, compared with the flat metric. And related to that is an important kind of general principle, which we'll maybe see later, that if we're looking at the sections of L to the k, the kth power of our basic line bundle, then we can detect with those the metric geometry of X on length scales down to the one we mentioned, order k to the minus 1/2. So that's our discussion of item 1. The way we want to find approximations to our Kahler metrics, or any Kahler metric at this stage, would be to use these algebraic metrics given by projective embeddings. So then the question is, how are we going to find, within that class of possible approximations, how are we going to find good approximations to our metrics we're interested in? So there are many ways one could go about that, and I think we'll maybe hear about perhaps different ways in the talks to come in this workshop. One way we could think about it would be that, for example, that the constant scalar curvature metrics are minima of a functional. It's called the Mabuchi functional. So we could restrict that functional to our finite dimensional space of algebraic metrics, which just correspond to given Hermitian metrics on a vector space, and then minimize this restricted Mabuchi functional on that finite dimensional space by some means. And if you could do that, if you could find those finite dimensional minima, then I'm not sure this is a theorem, but anyway, those would almost certainly converge rapidly in the sense of to all orders to the constant scalar curvature metric. And there's a similar discussion in the Calabi-Yau case, or again, other discussions for Kahler-Einstein metrics in general, with various functionals which play an important part in the theory. What we're going to talk about for the rest of the talk is some explicit sort of iterative procedures which produce approximations. And this is not completely disjoint from what we've been saying above. It's just a slightly different way of going about things. So for that, I need to launch into another section of some background. So this is called moment maps and geometric invariant theory, though in fact, actually neither of those things is going to feature explicitly in what we're saying, but those are the sort of big bits of theory which go under those headings, which are very relevant to what we're saying. So let's think about a kind of a toy model. Supposing we have a finite set in the true sphere, we have some distinct points, so at least more than one. Then it's the fact that we can move those points by a Mobius map, so that after moving the points, we get what I'll call a balanced configuration. So we start with some points pi, we move them to some points p prime di. By a balanced configuration, I mean that the center of mass of p prime di is 0, where we think of S2 as sitting in R3 in the standard way. So this is let's just say, so this sum of the points of the points pi appears as a moment map in a certain way of viewing the situation. But that's not so about it. So this is also connected to the complex geometry. If we think of S2 as CP1, the projectivization of C2, then if we choose representatives, capital Pi in C2 for these points of projective space, then we define a function given by the sum of the log of the squares of the norms of the Pi. Then we consider the action of SL2C acting on such d-tuples of points in C2. And then the balance configuration that we seek just corresponds to minimizing this function over an SL2C orbit. See, we have some choice of how we choose these representatives, capital Pi, but they only change the function up to a constant. So that makes sense. So more generally, what is the general story here? That if we take projective space of any dimension, complex projective space, it has an embedding, a standard embedding in the Lie algebra of SU n+1. So this was R3 in the previous case. So this is just the embedding as a co-adjoint orbit from one point of view. So if we have any measure, very general setting, if we have a measure on CPN, we can say that this measure is balanced if its center of mass in the vector space, in this Lie algebra, is 0. So in the previous case, we're considering just the measure given by point masses at these points, the pi. But under very mild hypotheses, then it's a fact that we can do the same thing. We can find under the complex group so that we can move our measure to a balanced one. And this, to see that, one can write down a function on SLM+1 similar to the function f, and you find this balanced point by minimizing that function. So then we can, this is what we're saying is immediately appropriate to the Calabi-Yau situation. If we have a manifold with first Chern class 0, so as we mentioned, it has a measure on it, just recall how that goes. So, well, strictly, we're supposing we have trivial canonical bundle, which is, you could have achieve that by going to a cover. So you have a trivializing holomorphic section, a holomorphic volume form theta, and then your measure is given just by theta wedge theta bar up to some constant depending on the dimension to make it a real number. So let's suppose we're in the situation as before. We have our line bundle L, and then we're getting embeddings of our X in projective space. But now we can take our measure on X and regard it as a measure on the projective space, just as we took our finite set of points and it defines a measure on the sphere. And then the theory we've outlined above means that we can move X by a projective transformation to a balanced embedding, as we have a preferred way of embedding X in projective space. So we get a Kahler metric, say omega tilde k on X, by taking the restriction of the Fubini-Studi metric to this balanced embedding, and again normalizing, multiplying by k to the minus 1, so that we stay in a fixed Kahler class. So this is a very, very sort of elementary construction. None of the proofs of all the statements I've made are in this bit of background are quite easy. But there is a sort of simple to state connection with the Calabi-R metrics, is that it can be shown that these omega tilde k converge to the Calabi-R metric on X in the given cohomology class as k tends to infinity. I say this does, and the different parts of that statement are different order of difficulties. In particular, you need to know there is a Calabi-R metric. It would be nice to be able to prove a priori that these sequences converged and obtain another proof of Yau's theorem, but I don't think anyone knows how to do that. But I say some parts of this are easy to see. Supposing we knew or believed that the omega tilde k do converge, then the fact that the limit is a Calabi-R metric follows quite simply from our discussion of the asymptotics of the BK, just from the fact that so the point is that the metric omega tilde k, if you unwind the definitions, you find by the fact the property that BK is a constant. So if we feed that into the asymptotic formula, we see the limit must have the metric defined by the Kahler metric, the volume form defined by the Kahler metric must agree with the given volume form mu that we have. And there's a similar story for the constant scalar curvature case. Now we don't have a measure, a volume form on X given to us, but we'll say X in C, we call a subvariety X in CPM balanced, again, at the center of mass of the measure which we get by restricting the Fubini-Studi metric is 0. So now there's a bit rather more subtle theory in the fine dimensional situation of this, that we can move a variety to a balanced one by a suitable projective transformation, if and only if it's what's called Chow's stable. So this is the connection with subject to what's called geometric invariant theory. But okay, so leaving aside and saying anything more about the theory, assuming that Chow's stability does hold, then we get a sequence of metrics omega tilde k in the same way, and it can be shown again that if X has a constant scalar curvature metric, then these omega tilde k converge to it. at least, so more precisely, maybe for safety, we should say this is known if X has no holomorphic automorphisms. So as before, parts of this are relatively straightforward, coming from Liu's result that the scalar curvature appears in the first first interesting term in the asymptotic expansion. So now then the question is, let's fix K, and so how are we going to find these omega tilde K? How are we going to find these particular algebraic metrics for fixed K? So there's a very straightforward sort of way of doing that by, well, in principle, via an actual iterative scheme. So to think about that, let's say, so we have really two kind of spaces in question. We've got the infinite dimensional space of Hermitian metrics on our line bundle, and the finite dimensional space of metrics on our vector space of sections of the kth power of our line bundle. And all we're doing sort of revolves around the interaction between those two things. And there are two, my way of saying it is this, there are two constructions, basic constructions. One is a map from the space of Hermitian metrics, MK, a fine dimensional thing, to the infinite dimensional space, and the other is a map in the other direction. So the first one, what is the first one? The first one, we have a metric on our space of sections, so that gives us a Fubini-Studi metric on the manifold, by restricting the Fubini-Studi metric, and in fact also defines, in a similar way, a Hermitian metric on the line bundle. So that's a way of going from the fine dimensional space to the infinite dimensional space. The other, if we start in our infinite dimensional space with a metric on the line bundle, then we have an L2 metric on the space of sections. So we get a map in the other direction. So if we take the composition of these two, we get a map, say T, from the space of Hermitian metrics on this vector space to itself. And one can show that if you take any starting point, any Hermitian form, and then just iterate this map, it will converge to a fixed point, and this fixed point corresponds to the balanced embedding that we seek. And then there's exactly the same discussion holds in the Calabi-Yau case, except that in our map from script H to MK, we use the L2 metric defined using the given volume form on our manifold. So putting this together, we have explicit schemes to find these Calabi-Yau metrics and constant scalar curvature Kahler metrics, at least when they exist. First of all, for each fixed K, we do this iteration to find the balance metric, and then we let K tends to infinity to find arbitrarily good approximations to the solution of our PDE, to our differential geometric objects. So, as I said, there are quite a few stories which this always interacts with, one like geometric invariant theory, moment maps, and so on. And there's a connection with geometric quantization, in that these passing from the, well, yeah. So let's just say the space of sections can be thought of the Hilbert space associated to the symplectic manifold given by our Kahler manifold, and the parameter K, the inverse of the parameter K, is plays the role of Planck's constant. But let's not go into that here. So the attraction of this for me is that this iteration is such a simple thing, so that even I can sort of imagine doing it on a computer. So let's just, leaving aside all the theory, let's just say explicitly what this means. So we'll do it in the Calabi-Yau case. So we're fixing K, we take any basis for the space of holomorphic sections, and supposing we start with a Hermitian metric on this space. So it's a matrix, sorry, there's a misprint there, G alpha beta. First step, invert that matrix. So this corresponds to going to the dual space. Next step, we define some functions, f gamma delta, again on x, given by this formula. So we take this denominator d is given by taking this gadget here, this summing with this inverted matrix, and then this is what we have. So this is, the notation here is sort of imagining that these sections are functions. And this is how it would appear if we had a local trivialization of our line bundle. But if you look for a moment, you see in the nature of things that the formula makes sense, makes invariant sense for the line bundle. So you do that. Next, you integrate these functions with respect to your fixed measure mu over x. And then you get another matrix, G tilde, with lower indices. Oh, but you multiply that by a normalizing constant for simplicity. This is just normalizing, so the trace of G tilde with respect to the original G is n plus 1. So that's it. The iteration step is to go from the matrix G you started with to the matrix G tilde. So if you've got a button that inverts a matrix and a button that integrates over the manifold, then that's all you have to do. In the constant scalar curvature case, there's a bit more, because you have to compute the Fubini-Studi metric at each stage, which will be determined in a more complicated way by your metric G. And this extra complication sort of reflects the extra complication of the problem, the fact that from the PD point of view, you're solving a fourth order equation rather than a second order equation. So what I've hoped to have described is a way, as it were, in principle, of finding numerical approximations to these metrics. And in a moment, we're going to see some examples, if time allows. But let's talk about the drawbacks, the limitations of this approach, of which there are at least two. First, limitation A is that if we do it this way, our approximations omega tilde k will, apart from very special cases, only converge slowly to the metric that we're interested in, only as order k to the minus 1 or something. In fact, the rate of convergence one can more or less see from the next term in the asymptotic expansion of the Bergman kernel. So, on the face of it, if we just do what we've said, this will not give us very efficient approximations to our metrics. If we want, let's say this space of sections has got dimension of order k to the n. So if we say we want to get an approximation 10 times as good, so we want to multiply k by 10, our matrices will be getting much, much bigger. So we don't, in practice, we don't want to take k to be some enormous number, because it would introduce new difficulties, shall we say. However, if our omega tilde k are just reasonable approximations to the actual solution. Then one can use some different approaches, a kind of Newton method, to find better approximations within these algebraic scheme, like the omega k that we discussed before, which should converge to all orders. And in practice, one finds that this is often the case, that if we take a small value of k, the omega tilde k is not super close to the actual solution, but it's reasonably close, reasonable enough to use kind of linear techniques to find much better approximations. The other limitation goes back to what we said about the link between k and scale. So supposing we have a part of our manifold where the actual metric we're interested in has large curvature, say of size order number c. So the natural length scale there on which we can sort of study that piece of the manifold is order c to the minus 1/2. That's where, if we scale it up by that factor, the metric will look roughly flat, roughly speaking. So combined with what we said before about the link between k and length scales, that means we would need to take k to be roughly of the order of c in order to study that part of the manifold. So, as we'll see an example presently, I hope, if there's some possibly small region in the manifold where the curvature is large, then to study that, to get good approximations to the metric there, we would need to take some large value of k, which is very likely impractical. On the other hand, very often on the bulk of the manifold, we have a much smaller value of the curvature, and the metric there can be effectively studied using a smaller value of k. So maybe in the context of a lot of the work and discussions in this collaboration, you can say that the method we've been discussing it's well suited to trying to study points deep inside the moduli space, where the curvature is roughly constant, doesn't vary too much. So it's kind of opposite to the gluing type techniques, which we often talk about in this collaboration, where one is studying points near the boundary of moduli space, where we have some high curvature region, for example, using gluing techniques. So this limitation B is an essential difficulty. It's a possible approach is to combine using different values of k over different parts of the manifold. And I think possibly this will be something that comes into other talks on this topic in the meeting. So we've just got about 10 minutes, I think, to finish off. So let's talk about some examples. So here, I said I'm going to be doing some jumping around because I had some problems with putting diagrams in my PDF file. So let's talk about, we're going to talk basically about toric manifolds, particularly toric surfaces. So remember, a toric manifold has associated polytope in Euclidean space, and everything works very nicely there. You have a basis of sections of L to the k corresponding to the lattice points inside the polytope when we take the integer lattice and scale it by a factor of k to the minus 1. And then what makes, one of the things that makes things work easily here is that all our metric matrices are diagonal in this basis. So we don't have, inverting the matrix is straightforward because it's just a diagonal matrix, for example. So we're just talking about toric surfaces, and there's some interesting, just to digress for a moment, really, there's some interesting differential geometry on a toric surface. But there we have a polytope is just a polygon in the plane, and in fact it can be embedded inside the complex surface, or more precisely a fourfold cover. The polygon is embedded as a totally geodesic submanifold inside X. And then the differential geometry of X can be analyzed in terms of four components of the curvature tensor, one of which is the scalar curvature. The other is the Gauss curvature of this surface inside X. Then there are two other things, which is, one is a quadratic differential, which corresponds to the trace-free Ricci curvature. And then the Weil curvature now appears as a quartic differential on the surface. So we said we want to try to understand these metrics on these toric surfaces. So we'd like to be able to compare between them. So it's useful to normalize the scales so we get some sort of sensible comparisons. So in all we're going to talk about, I'm normalizing so that the average value of the scalar curvature is 1. So for example, we could take complex projective plane, CP2. The only non-zero invariance, of course, S is 1. Like what we said, this Gauss curvature component is 1/6, it turns out. While for S2 times S2, the non-vanishing component, apart from the scalar curvature, is the W component, which is, has got size 1 over the square root of 8. So, yeah. So what we might call the hexagon manifold, because its polygon is a hexagon. This is maybe the simplest Kahler-Einstein manifold, which somehow doesn't have an explicit description. There's no explicit formula for the metric. So the existence of this metric was proved by Tian and Yao and Hsu at the same time. It's just so as a complex surface, it's just the blow up of the projective plane in 3 general points. So by following through the kind of ideas that I've outlined, you can work out everything you like really about the curvature tensor of this metric. So see the maximum value of the Riemann curvature tensor is this, the minimum value is this, it varies by a factor of about 4. This Gauss term K is always non-positive, but its maximum value is 0, then it goes down to minus 0.82, whereas this Weil component is quite big. Because this is a Kahler-Einstein metric, the trace-free Ricci is 0. So these are obtained using the procedure I've discussed, taking K equals 20. But one can actually get quite a good approximation to the metric just using a much smaller value, K equals 6, in which case, taking full account of all the symmetries present, there are only 6 independent matrix entries that you have defined. So now, it's the time here, maybe just about time to do this. Can I go a couple of minutes over because of the layout? What do I do?
Sure.
Press.
Yeah, I have trouble unmuting. Yes.
Yeah. So let's see what this is going to work. Yeah. Okay. So this is apologies for this not very good presentation. Maybe you can. So this is the picture of this hexagon, and then the number. So we have this. Everything is determined by this metric on this vector space, which has got a basis indexed by these lattice points here. And the metric is diagonal, so we just have to give a number for each of these lattice points. But then there's a kind of, well, there's lots of symmetry. It's not entirely apparent in this hexagon. So a lot of these numbers are the same. The numbers at the corners are the same, and the numbers on the edges are the same. So there are 6 numbers, which, if you find them, you get quite a good approximation to this Kahler-Einstein metric. So is that going to close that? Go back here. What are we doing now? So now, if we take another toric surface where the polygon is a heptagon, which I'm going to show you in a moment, then so this is you'll be blowing up. In fact, you blow up some points and then blow up. You do some multiple blow-ups of the plane. So this, in fact, has an extremal metric. It's not exactly constant scalar curvature, but for our purposes, you could think of it as the same. The theory goes exactly the same way. That's got, after this normal, that's got much bigger curvature, you see. It differs by the factor of almost, 20 or something. And then you have all these different components. This is not Kahler-Einstein, so you've got some trace. So this is an approximation obtained using k equals 45, because, as we said, the curvature is bigger. To get good answers, you need to take k larger. So again, if we can do this jiggling around, yeah. So we go to this one. Okay. Okay, maybe I can make it bigger. Zoom. Yeah, okay, it's probably a bit hard. Anyway, this is the heptagon, which corresponds to that manifold. So it's got the numbers written here. I'm not sure you can see them with my incompetence with the screen. These numbers are the self-intersection numbers of the components of the sort of boundary divisor. So this has got a curve of self-intersection -3 here, unlike the previous case. The previous case we had just I guess -2 curves corresponding to the boundary. Okay. What have we got next? So finally, we're finishing off. So beyond the toric world, again, you'll hear more about much more complicated and better things in other talks. But I developed these ideas in a simple case of a K3 surface. If you take the one which is a double color of the plane branched over especially symmetric curve of degree 6, given by x to the 6 plus y to the 6 plus z to the 6 is 0. So again, your holomorphic sections you can write down quite explicitly. You take the square root of d formally, and then you take p plus q times the square root of d, where p is a polynomial and homogeneous polynomial x, y, z of degree k, and q has got degree k minus 3. So one finds what I can get using completely, essentially elementary computing techniques, which is indeed all I'm able to use. One gets a reasonable approximation to the Calabi-Yau metric on this K3 metric using quite modest values of K. And again, in view of the large symmetries that one has, there are, again, just 11 matrix entries that you need to find. So the computations are, in the end, quite tractable. So let's just finish by looking at that one. Which is that one? What's this one? Oh no, so okay, so there's one. I think there's one out. Yeah. So this is a picture. This is a diagram which illustrates the matrix entries which determine you have to think about in order to construct this metric on the K3 surface. So you have your polynomial degree 6, but again it has lots of symmetries, so a lot of these coefficients are the same, and a polynomial degree 3, which again has got some symmetries. But let's just finally, before stopping, there's something I forgot to show you about this heptagon manifold. So yeah, this is a graph, and I fear you won't be able to see it very well. Now, this is a graph of the size of the Riemann curvature on this manifold correspond to this heptagon. And it illustrates the fact that the curvature, as you can see, is much bigger over a small part of the manifold than over the majority of the manifold. So the curvature, this is roughly the value 1. You see the size of the curvature. But it shoots up as we go to the boundary of the heptagon, particularly over the -3 curve in the boundary. So, and other things that one can do. So the main point I want to say is that it is, I think it's an interesting direction in differential geometry to try to really know what these metrics we talk about look like, and that it's something that can be done, and that the techniques that can be done using essentially, at least in some cases, using quite elementary techniques, and that there are interesting interactions between the techniques and various other theoretical considerations like invariant theory and moment maps, geometric quantizing, and so on. So, thank you. I'll stop there.
Thank you, Simon, for a very fascinating talk. Let's all show our appreciation for Simon's talk. And perhaps Simon would be willing to entertain a few questions.
Of course.
I won't. Dan?
An incredibly naive question, but in case where there is not a Calabi-Yau or constant scalar curvature metric, and one runs this iteration scheme, does anything interesting result?
Yeah, so the answer is yes, it should do. So in the Calabi-Yau case, essentially they always exist. So yeah, but in the other case, then indeed they don't always exist. So right, there'll be a discussion about whether the convergence fails at finite k, or whether taking the limit as k tends to infinity is what fails. And that is related to, in algebraic geometry, the connection between what's called k stability and asymptotic Chow stability. But I think in principle, either could happen. You know, either kind of failure could happen. I haven't been able to, you know, I tried but never succeeded in producing examples of such failure of convergence. I think because to find examples, one needs to take, in a sense, rather complicated manifolds, which go beyond beyond my techniques. But certainly that should be possible and interesting to do. Maybe I could also mention that these iterations are related to natural flows that one has, like the Calabi flow and the Ricci flow and so forth. And discrete versions of the flows.
Other questions? Raise your hand or
Can I ask something, Robert?
certainly, Bobby.
I mean, so it's slightly, I mean, certainly beyond the context of what you were talking about, Simon, but do you have any ideas, even vague, any suggestions for doing numerical approximations for, you know, outside of the Kahler world, in particular, you know, exceptional holonomy?
Well, I do have an idea. I was talking to Robert about it just a few weeks ago, but it's a completely undeveloped idea. So I don't whether it's a good idea. I don't really know. But it's based upon a 5-dimensional approximation to Hitchin's functional, shall we say, is in the G2 situation. So if you have that would be a different. This would be in the context of a triangulation of a manifold, a kind of a simplicial version of Hitchin's theory. But that would be it would be interesting to have further discussions about that, and maybe someone to help develop it.
Yeah, that sounds good. Maybe we can discuss it later.
Right. Other questions?
This is a slightly vague question. Could you imagine that there's some theorem or sort of is there some way that the numerics could play back into the theory in some way? Is there any? I mean, and all the theory is very well developed, what you described, but is there something that could come back from doing some of these numerics? Or
well, I think so. And for one thing, at least at the time that these papers were written, I mean, the existence of those extremal metrics, for example, was not known theoretically. So, yeah, and I think I didn't have time to mention it. There are these things called deformed Hermitian-Yang-Mills equations, which there's a lot of interest in. Not something I know really much about at all, but where I think there's not much theoretically known about general existence theorems, but maybe one can use these kind of techniques to study existence questions numerically, and that might suggest what should be true. Yeah.
Thanks.
Let's see. I don't see any more hands raised, so let's thank Simon again for a very stimulating lecture. And we now have a break until